Hello students, welcome back. Let us resume our discussion in section 3. Previously, we completed this example problem. Remember? If a and b are integers and the GCD is d, then we can create a pair of integers that are relatively prime by dividing a by d and b by d. Remember, d is a common divisor, so a over d and b over d are both integers. We ended up with a pair of integers that are relatively prime. And the proof, okay, all right, we went through that already, so let's just review that. And we can utilize this to prove that any fraction, any non-trivial fraction can be reduced to the lowest terms. Any a over b, any non-trivial a over b can be reduced some p over q where p and q are relatively prime. All you have to do is to divide both the numerator and denominator by the GCD. So a divided by the GCD d and b divided by the GCD d. And did you prove already that a over d and b over d are relatively prime? Yes, we did. So the resulting fraction is the simplification to the lowest terms. So the simplification to the lowest term is always possible. How about this? Do you remember this? C is a common multiple of a and b are relatively prime, then C is divisible by the product a times b. That was a bit trickier, but not too bad. Now this, I think, was the hardest of the bunch, and also the most important of the bunch. It is known as Euclid's lemma. Whenever you encounter something that is attached to a name, then that's important. And yes, that too is important. This is not an exception either. A divides b times c, and a and b are relatively common. So a has nothing to do with this part, so entire a must divide c. That's the idea. It's called Euclid's lemma, and the proof is a bit trickier than the others, hardest of the bunch, but also the most important of the bunch. As for the proofs, I'll leave those to you. I mean, if you go through this notebook and open up the hidden cells, yeah, you can find most of the proofs. 90% of the proofs you can find from those hints, but I'm not showing you here. I want you to work out. Okay, that's where we left off. Let's continue. How about part A and part B? N is even if and only if n squared is even. We went through that already in section 1. N is odd if and only if n squared is odd. That's actually contrapositive of the first, so that's equivalent. Again, we went through both in section 1. How about this? Did you go through this already in section 1? Yes, we did, but we left a hole there. Remember that hole? Yes? No? Maybe not? Well, let's have a recap. We have to prove square root of 2 is rational, and here's the setup. We put square root of 2 as m over n reduced in the lowest terms. But wait a minute, is this always possible? Can we always reduce any fraction to the lowest form? Yes, we can, and we proved it right here in 3.4b. So in section 1, we actually skipped this part. I didn't mention it because I didn't want to get too distracted by this. But now we can mention it. We established this Bezoos expression, the linear combination expression, and then we use that to establish relatively prime, and we use that to prove part A, and we use that to prove part B, and that's what we are using here in this example problem. So the fraction already reduced in the lowest terms is always possible, so let's start from there. And then we can derive some contradictions out of there. Square both sides. 2 is m squared over n squared, so m squared is 2n squared, so n squared is even. Consequently, n is even, and here's the proof of the contrapositive. So m is even, so plug in m is even there, 2a there, then we have 4a squared like this, and plug in with this n, then we get n squared is even. Therefore, n is even as well. So what do we get? We get an even or even. So we ended up with another fraction that is reduced even further. And there goes the contradiction, because we started from the lowest terms. It turned out it is not the lowest term. So there goes the contradiction, and we have the proof by contradiction completed. And remember, the starting point here, whenever we have a rational number, it can be expressed as an integer over integer, but not only that, that's the definition of a rational number, by the way, but can it be written in the lowest term? Well, we have the proof now, and the proof was done here, 3.4b, using the GCD concept, Bezout expression of relatively prime, which came from Bezout expression of GCD, the linear combination. Amazing, they're all related. Okay, alright, one more. Let's go one step further. A real root of a monic polynomial of integer coefficients is either an integer or irrational. What do you mean by that? That's what it means. Alpha is a real, yeah, it's a real, and it's a root of a monic polynomial. What is this expression here? So this kind of thing is called a monic polynomial. A leading coefficient is 1. So in general, we have something like this, then it is not called monic. Mono means 1, so I have to start from 1. So if this is 1, then it is called monic, and 1 times something, we don't usually write like this. This is a monic polynomial of degree n. So alpha is a zero of a monic polynomial. That means it has to satisfy this equation. And the theorem says, if so, then either alpha is an integer or an irrational number. Before proving this, let's consider an application of this. Let's consider a special case where all the middle things, they're all zeros. And then replace c0 by negative c, then you're going to get alpha to the nth power minus c is equal to 0, or equivalently, alpha to the nth power is equal to c. And what does it mean? Alpha is an nth root of c. Let's go back to where it was. It's the nth root of c. And alpha is either integer or irrational. So this is a stronger result compared with this one, because this is just square root. And this one is about not just square root, but arbitrary nth root. And here this one was about just 2, but this could be any c as a matter of fact. And if that c is, say, a square number or cube number or a quarter number, whatever, in that case, here we have an integer, but otherwise all irrational. And of course, this one here is even stronger. So sometimes it's easier to prove something stronger. This is one of those cases, and let's prove it. How do you prove that? Well, let's begin with an assumption that alpha is a rational number and put a over b in there in the lowest terms. So GCD of a and b is 1, and alpha is a over b. Plug it into this. So we have a over b to the nth power, and then n minus first power, n minus second power, and so on and so forth. So alpha is replaced by a over b, so that's it there. Now let's simplify this. Too many denominators. This is number theory, so we want integers. No denominators. One way to kill them all is to multiply b to the nth power to everything. If I do that, I'm going to get this. I agreed. Multiply b to the nth power to kill off this. Multiply b to the nth power, then n minus first power gone, and we have 1 left, and so on and so forth. So all these have some powers of b. And I'm going to flip all those to the other side. You're going to get this. Actually, I'm skipping a step. So let's write like this and flip everything to the other side. And then everything here becomes subtraction. Okay, there you go. If I flip everything to the other side, this is what you're going to get. And I factor b out. That's what you're going to get. Now this expression here looks complicated, but it's an integer. So some integer times b, that proves b divides a to the nth power. All good? Does it make sense? Okay, now from here we can apply Euclid lemma. How do we apply Euclid lemma? B divided a to the nth power means b divides a times a to the n minus first power. Now, a and b are relatively prime, right? So these two have nothing to do with each other, so b must divide the other one. Oh, if it divides n power, then it divides n minus first power. Nice reduction. We can do this again. B divides a times a to the n minus second power. Again, Euclid lemma. A and b are relatively prime, so b must divide this. If I repeat this over and over again, eventually, what do you think you're going to get? It divides a to the third power, a to the second power. Eventually it divides a. But that's not possible, you see. A and b are relatively prime. So this is a contradiction unless b is 1 or negative 1. In that case, the denominator is 1 or negative 1. So the fraction alpha b over a is an integer. I have written everything here in a bit more formal fashion, but yeah, I wrote a bit too much. Simplified version looks better to me. So this contradicts the assumption that original fraction is in the lowest terms unless b is plus or minus 1, so that there is no need to reduce anything to begin with. In which case, of course, alpha, which is a over b, but denominator is 1 or negative 1, so it's an integer, so alpha is an integer. So if it is integer, then fine. Non-integer rational number, then not fine. Contradiction. So what conclusion do I get? The result is either an integer or an irrational number. And we already went through the remark here. So this is a stronger result compared with part C. A lot stronger, as a matter of fact. Okay, so much for this example. And we have some further properties of GCD, which I'll leave as an exercise for you as homework problems. And that'll conclude section 3, except the proof of Bézout's theorem, which we are going to cover in the next video.